To find the inverse of a symbolic function, we want to stay in keeping with the idea that we swap our input and output variable. In this first example, we can think of that as just being y equals the cube root of x plus 1, changing our f of x to a y. And since this is a generic xy sort of context, we can swap which is the input and which is the output variable by just changing their names. So I am going to change my y to an x and change my x to a y, which makes now what was y the input variable and what was x the output variable. So I'll rewrite this as x equals the cube root of y plus 1. At this point, it is now the inverse function, but we're not done until we can write it as f inverse of x equals, and in order to do that, we have to solve it for y. So I can see that now I identify my y, I locate it, and I start the process of solving for y. We'll start simple. That plus 1 we can move to the other side by just subtracting 1 from both sides. So that is going to give me x minus 1 is equal to the cube root of y. And then I again focus on where my y is. It's inside a cube root. The way that I would undo that cube root is by raising both sides to the power 3. So when I raise both sides to the power 3, I end up with x minus 1 quantity cubed is equal to y. Now that I have this solved for y, I would write it as a function. My y is now f inverse of x. And my formula for calculating the inverse comes from the other side. Note that we can also think about the verbal description to help us find this inverse. If I go back to the beginning and just look at my function and describe it verbally, what it does to x, and describe it in the correct order following order of operations, I would say this function takes the cube root of x and then adds 1. If I want to invert each operation and reverse the order, I would first subtract 1, which I see right here. And the second thing I would do is the inverse of the cube root, which is to cube the whole thing. That's why my cube applies on the outside of these parentheses instead of just to the x. Now if we take another example, we're looking at a formula that converts temperature in degrees centigrade to degrees Fahrenheit. This is just an equation, right? It's not written in function language, but we can see that f is a function of c. I'm not going to change the names of the variables here because f stands for temperature in degrees Fahrenheit. C stands for temperature in degrees centigrade. They don't change their meaning when we take the inverse. So I'm going to leave the variables as they are, and in this case, just solve for c. So I'm changing my designation of which of these is the input variable and which is the output, but there's no need to change the names of the variables this time because we're not in a default xy context in which x is the input and y is the output. So we just solve for c. We'll start by subtracting 32 from both sides. Which gets us f minus 32 on the left and 9/5 c on the right. And the easiest way to finish this is to just multiply both sides by the reciprocal, which is 5/9. No need to distribute this fraction into the parentheses. Since it's just going to create a messy fraction for that second term, we will go ahead and leave it in this form and just say on the right hand side we can see that everything cancels except for c, right? And that's why this works. And our function now is just c equals 5/9 times f minus 32. So in general, we want to remember that we do swap the variables if they're x and y, and if it's assumed that we want to stay in that default x is the input, y is the output context. In any other situation, you probably do not want to change your variable names. You just want to solve for the other variable. All right, next we have a kind of fun little example of two functions which we claim are self-inverses, and we're going to see exactly what that means as we start working with them. The reason we're showing these is that sometimes when you're trying to find the inverse of a function, you go through the process that we just described, and you end up getting the exact same function that you started with. And that can be a little bit confusing, especially if you're not sure maybe if you made a mistake or if you forgot to swap your x and y or something like that. So we're going to look at these two forms. These are the most common and simplest forms that come up of self-inverses. We're going to look at these two forms and see why it is that they are their own inverses. If I take this g of x and just replace g of x with y to write it as y equals 6 over x, and I'm not trying to find the inverse yet, I'm just trying to illustrate something. If I clear the denominator by multiplying both sides by x and write this in a different form, these x's cancel and I end up with x times y is equal to 6. Now remember that the way we find the inverse, if we're in this context, is we either swap the variables or we just solve for the other variable if we don't want to swap our variables. In this case, I would swap them. Looking at the form of this though, if I swap x and y, I can see that I'm not really going to get a different equation. Because multiplication is commutative, when I swap x and y, I don't change it, and therefore swapping x and y and then solving for y is going to give me the exact same function that I started with. Therefore, it's also true, in addition to the fact that g of x is equal to 6 over x, in fact g inverse of x is also equal to 6 over x. And let's try it out. Let's just come up with a number, maybe a number that divides evenly, just to make it simple, like say x equals 3, just for example. G of 3 is equal to 6 over 3, which is 2, and then g inverse of 2 is equal to 6 over 2, which is 3, right? So what we can see just happened here on this example is that 3 is the number I started with. I applied the function g, and then I applied the function g inverse to its output, and I got back that same 3 that I started with. So I can see that the function 6 over x does in fact undo itself. And with this numeric example, I can get a better idea of why. A very similar thing happens with h of x. If I again start by just replacing h of x with y, and then I change the form of it by adding x to both sides of the equation, what I get now is x plus y equals 8. Well, multiplication is commutative. That means if I change the order, it doesn't really change. Addition is also commutative. So if I change the order of x and y, I don't get a different equation. So this is another example in which the inverse function, h inverse, is the same as the original function. So if you find an inverse of something, maybe you didn't think of this first, if you find an inverse and what you're finding is that it looks an awful lot like the function you started with, it might be the case that your function is of the form a constant divided by x, or of the form a constant minus x, in which case you can expect that it's a self-inverse. There are others as well, but these two are the most obvious, most common.